Hey everybody, welcome back to Organic Chemistry. Now we're going to go over the Diels Alder reaction. So this is section 4. And basically this reaction is kind of interesting. Everybody seems to love it, from professors and students alike, because from a professor's point of view, it's got a lot of interesting chemistry, okay? A lot of different things going on. From a student point of view, it's kind of fun once you get it, and it's a lot easier. You know, when you first start learning it, it's a lot of details, but once you get it down, it's kind of fun and it's pretty easy to do, okay? But it just takes a little bit of practice and a little bit of patience. Okay, so let's get started. The first thing, number one, is let's talk about the general concepts. Okay, so what is this all about? Well, this is called an electrocyclic reaction. Electrocyclic reaction. And what this means is as in electrons, are moving around in a cyclic formation. Now, there are several different electrocyclic type reactions, but they all have one thing in common. Electrons move around to form a ring. Now, there's cycloadditions, which is what we're going to do now. There's something called sigmatotropic reactions, which we won't talk about at all, and so on. There's a few others as well. But the thing is that they all have electrons that move around in space. So for our particular reaction, we need two things. We need a diene and we need a dienophile. And together, they will always make a 6-member ring. Now, this is so important because you're always going to make a 6-membered ring by doing this process, this Diels Alder reaction. Now, there are other types of electrocyclic reactions, and we'll see them towards the end of this review. But for now, we're going to focus in on the Diels Alder reaction. So the Diels Alder reaction, you have a diene and dienophile, and they come together with heat to make a 6-membered ring. Okay, so what is a diene? I hope you guys know a diene is a 4-pi system. And a dienophile, which you definitely don't know unless you read the book and you've seen the class, is a 2-pi system. So we have a 4-pi and a 2-pi that are coming together. So for example, if I have, let's say, a diene and I'm drawing it like this, and we'll talk about why in the next section, this is a diene. It's a conjugated 4-pi system. And if I react it with an alkene, which is a 2-pi system, with heat, then they'll come together. And here's how it works. You always want to number your diene, number 1, 2, 3, and 4. Then you have 5 and 6. Now, that's always the way that we're going to number this. We look for these numbers, actually. So when we work through problems, we always label out 1 through 4 and then 5, 6. The way it works is that in this case, it doesn't really matter in this case, but we're going to say that the 6 gives electrons to 1. 1 pushes its double bond away to 3, 2 to 3. And 4 takes its double bond from 3 and gives it to 5. See that? So there's no mechanism. It's an electrocyclic reaction. It all happens at the same time. So here's carbon 1, 2, 3, 4, 5, and 6. Notice that we have this double bond here going to the back. So we have to show that. And we have a double bond right there. So there's always going to be a 2-3 double bond at the end of this process. Okay? Now, we'll learn that you can get rid of the double bond in H2 palladium, things like that, but it should be there to begin. All right, another thing to note here is that this pi bond, this double bond, disappears, right? It was a double bond. Now it's between 5 and 6. It's just a single bond. And that's the electron flow. So we're getting rid of double bonds and we're making sigma bonds. See that? We're making a sigma bond between 4 and 5 and 1 and 6. We're getting rid of 2 double bonds, one between 5, 6, and the other is kind of, it floats away from that diene. And this is the process. This is how it flows. Now, we have a diene and a dienophile. That's the idea. And you need the heat because this won't happen without it. You need to have temperature to make this electrocyclic flow. All right, now here's another example. So this is example 1. Now here's example 2. And I'm trying to declare all the different scenarios of the diene itself and the dienophile, like the common structural characteristics. Okay? So here's another example. We can have a diene, okay, and I have it in this special form, and we'll talk about why, where it's like where the double bonds are on the same side. Okay, we'll talk about that soon. Here's 1, 2, 3, and 4. But instead of a double bond, I can have a triple bond. Okay, this is an alternative. It's still a 2-pi system. There are 2 atoms involved with the pi system, but it's a triple bond. Now, what happens? Well, 5, we're going to do the same thing. 6 gives the electrons to 1. 2 takes a double bond to 3. 4 takes a double bond and gives it to 5. But at the end of this reaction, we didn't get rid of 2 pi bonds, only 1 from 5, 6. So here's 1, 2, 3, 4, 5, 6. 5 and 6 still have a double bond left at the end. And of course, there's a double bond between 2 and 3. Remember, this template is always the case. Double bond between 2, 3, and bond connection between 6, 1, and 4, 5. But notice that if there's a triple bond, then we wind up having a double bond at the end. See that? So that's another template that we have to keep in mind. Okay, there's one more example template that we need to keep in mind. So for example 3, what happens if we have this conjugated system, this diene, right, diene, but it's in a ring? So we have that right there, and we could do anything we want. Let's make it an alkene like ethene with heat. Well, how does this work? Well, it's the same thing. You always look for your 1, 2, 3, 4 in your diene, and your 5, 6 in your dienophile. So notice if I numbered left, top left, number 1, it would be wrong, right? Because if I numbered the other way, if this was 1, 2, 3, 4, 5, you wouldn't have your diene anymore. You need a 1, 2, 3, 4 double bond. So that's why I know I have to number it the other way. Okay? So this must be 1, 2, 3, 4. You're always looking for the pattern of a 1, 2 double bond, 3, 4 double bond. Okay. Now, what do we do? Well, there's this one carbon right here, this red carbon that's pointing in between 1 and 4. Well, the way that we handle that is that we draw this in a perspective drawing. We could draw a 6-membered ring. So I could draw it like this, where 1, 2, 3, 4, 5, and 6. So there's a double bond between 2, 3, right? There's electrons going here, electrons in the back, electrons going out. Okay, just like that. You don't really need to show the arrows, just so you know. Okay, it's just that I'm kind of getting you used to the idea. So we have 1 to 6, 4 to 5, 2, 3 double bond. And what do we do with the red carbon? Well, we could just simply put it right in the middle, like that, between 4 and 1. So right there is the red carbon. See that? So all we did is we started by drawing a 6-membered template, and we plugged in the extra carbon in between. This is one way to draw it. Another way to draw it, which you have to get used to, is on a perspective, on like almost like a boat instead of a chair. Like we draw it like this, where it's kind of going up and then down, like that. Okay, here's 1, 2, 3, 4, 5, 6. There's a double bond between 2 and 3 as always. And now I could show straight up in the air the red carbon coming back down to 1. So these two mean the same thing. But it's more common whenever you have in your diene a carbon in between 1 and 4 that are connecting together into a ring, that you draw it in a perspective drawing like that. You can draw it like that, get full credit, but this is more likely how you would see it. Okay, so these two mean the same thing. So these are the 3 ways. Now again, we started with this very basic concept. It's an electrocyclic reaction. We showed the electron flow. It's always a 4 pi plus 2 pi. That's the name of this, 4 pi plus 2 pi. And it's a 4 pi plus 2 pi pericyclic reaction or electrocyclic reaction. Okay, and that's how we basically have this set up. So these are our templates, and this is what we're going to be working from to begin. All right, so now the next thing I want to talk about, number 2, is I want to focus in on the diene. Okay, so now we're going to break up the topic a little bit, and we're going to focus in on specifically the diene and learn about its concepts. Now the first thing I want to point out, and we'll learn about why a little bit later, is that the diene is considered the base. And we'll see later on that its electrons are higher in energy.